Sorry, back at this. Okay, so we're going to create our graph here. So negative x squared plus 4x plus 7. Okay, so here's our graph. I'm just going to zoom out just a little bit so we can see what it looks like. A nice little quadratic. Just going to give a little sketch here, just like we did with the other ones. And something like that. And there you go. We can read off the graph here. You can see right there, the 0, 7. Click there. Yeah, 0, 7 is my y-intercept, which might be useful for later. We got a couple of x-intercepts down here. They're not very nice. You can see here, not very nice numbers, but that's okay. Let's just go over to the next one here. Let's sketch this one out. This is positive 2x squared. Just emphasizing the positive there. It might be useful. And negative 5x, minus 5x minus 3. So here's my graph. Okay. Let me just click a couple points on this graph so we can see what this looks like here. Well, this is much nicer x-intercepts. Give a little sketch. And we have a point here, 0, negative 3. Okay, so now we have these two graphs here. Let's analyze them and see what the differences and what the commonalities between the two. Before we start, I just want to talk about what is nothing, it doesn't say in here, but what is my leading coefficient? Because that's a pretty important indicator of what kind of graph, or what kind of characteristics this graph might have. First, now also both degree of two graphs, they're both quadratics. So let's see what we have here. We've got number of x-intercepts. Well, they both have 2. They don't necessarily have to have 2, because remember you can have a graph that's a little bit higher up. It doesn't cross the x-axis. We have an example of that earlier. Y-intercept. So we know the y-intercept of both these graphs. This one's at 7, and this one's at negative 3. That doesn't really help us too much, but oh, maybe it does. Look at this. So I got 7 here, and I have a 7 here. I have a negative 3 here, and I have a negative 3 here. Oh, that constant term seems like that's what that is. I'm going to back up here for a second. My constant term on this one is 0. You don't see it. If you don't see a constant term, you just assume it to be 0, and you notice that these are both 0. Constant term, y-intercept. Yeah, okay, that might be something that's useful. And behaviors. So this one starts off 1, 2, 3, quadrant 3, and ends in quadrant 4. And you can, if you want to, you can use numbers. You can say like this starts in quadrant 2, ends in quadrant 1. Domain, XER, and XER. My range. Now the problem with the range here, I need to know where the min and the max values are. I forgot to record the max value for that one. I didn't for this one here. You can see my min value is my y value here. I click it. It says negative 6.125. Okay, so this point down here has some x value, but then has negative 6.125, my y value. I'm just worried about the y value here. So it has to be everything greater than or equal to this number. YR. Cool. Turning points. They both have 1. Cool. Graph represents a quadratic. Quadratic. The same thing with this one. I got a oh, that's nice. Spell quadratic. Maybe you spell quadratic correctly. There we go. Quadratic. I mean, if I want to go back and try to find out what the max value is for this graph here, I can go back to Desmos here and type that back in there. So negative x squared plus 4x 7. There's my graph again. The point at the very top here. There it is. Oh, it's actually really nice. 2, 11. So 11 is the top point there. So this point up here. That's the highest this graph goes. So that means my graph has to be everything that's less than that value because it's from this point down. So that's my range. There you go. Now the leading coefficient for this one over here, the one on the left, is -1, and the leading coefficient for this one is +2. Now the key is the leading coefficient is negative, the graph is opening downwards, and the leading coefficient is positive, and the graph is opening upwards. You can see that in a few different examples we did up here as well. If I scroll up pretty far here, oh, I didn't give you the equation for these graphs. So I did here. So I have 2x squared. This graph is opening upwards. Okay. You can see that in these ones, the leading coefficient for this cubic one is positive, so it's going in the positive direction, like left or right, it's going upwards like that. Same thing with this. This is a positive slope, so it's going that way. Right? Okay, let's go back down here. Let's look at some other graphs. So we did some quadratics. Let's do some cubic ones here. There's some quartic ones. I might just skip over the quartic ones. We're not going to do quartic ones in this course. If you want to, you can analyze them as well. I'm not too concerned. I'm worried about going up to cubic graphs here. I probably should just erase those ones down there. Maybe I'll do that later. Okay, so let's look at these graphs. I'm going to just plug these into my calculator. 2x cubed, so these are the cubic graphs. That's the highest degree is 3. And there's my graph. That's what it looks like. Let's just stretch out, make it look a little bit nicer. There we go. Okay, so I'm going to sketch this here. I'm going to have my x and my y axis. And I can see that it's going to cross once, go down, then back up. It doesn't cross again. If it went down a little bit more, it could have crossed twice or just touched, but it doesn't quite touch there. Nothing else I need to worry about. Oh, I have some key points here. Like you notice here, 0, 2. I'll write that down. That's my y-intercept. Oh, I did a horrible job for sketching this out, apparently. 0, 2. You guys probably do a better job sketching that. The next graph here, we're going to put a negative in the front and see what that looks like. Cube plus 2 squared plus 3. Cool. Okay, let's see what this looks like. X and Y. I'm going to sketch this out. I don't know why this also changed color. There we go. Going down and down. So this point here is 0, 3. I have to look at the graph to do that. I can look at the equation. We'll talk about how we know that right away. So we have our cubic graphs here. Let's analyze these and see what they have in common. They both have one x-intercept, but they don't necessarily have to have one. Like we said previously, you could see some cubic graphs in some previous examples. Like this cubic graph has 3 x-intercepts. This one has 3. This one has 3. That one has 3. I drew some here that have 1 or 2 x-intercepts. So the cubic graph doesn't have to have 1. It doesn't have to have 3 either. Right? Y-intercept, 2. Y-intercept, 3. I'm just going to go back to what we kind of thought about before. Like there's a 2 here. This is a 3 here. Because there's a 2 here and there's a 3 here. So those match each other. Maybe seems like it's working pretty good. This one's going from quadrant 3 up to quadrant 1. And this is going from quadrant 2 down to quadrant 4. I got a nice little domain here, XER, XER. The graph goes up forever, down forever, with no holes in between, so those are going to be YER. You know, so pretty much the only ones I have to worry about my range so far are quadratic graphs. Turning points, 1, 2, 1, 2. Yeah, so 2 turning points each. And these are cubic graphs. Okay, so that's as far as we go. If you want to, you can analyze these. You plug them into your calculator, see what they look like. Not too concerned about these ones. We're going to go jump down to this table here, and I'm going to give you guys a little bit of time. I want you to think about, can you just look at these? If it is a polynomial, if it's not a polynomial, then don't do everything on this side over here. First of all, identify if it's a polynomial. If it is, fill out the rest of the table. If it's not, don't worry about filling out the table. Just say it's not a polynomial and move on to the next one. want you to try this out. Give you a little bit of time to do that. Let me just pause it right now. Okay, so hopefully did this. Let's go through. So polynomial function for the first one. Yes, it is. Technically, it is a linear one, right? Because the highest degree is 1. I'm just going to go down and determine if it's a polynomial first. This one is not a polynomial because it has a negative exponent. Bad idea, right? It creates an irrational expression, so it's not. So we're not going to actually do anything over here for this one later on. Let's cross that all off. This one is. Yes, it is. This is technically a quintic. You don't have to know that, but it's technically a quintic graph because it's power of 5. This one is not, because you notice that this x is in the denominator. That's not a thing for polynomials. This one is. Yes, it is. It's an octic one. You can see the highest degree is 8. Let me put that there. I'm going to put this here, and this one's a 1. Okay. Okay. This one has this weird bars. These bars are called absolute values, and the absolute values are not a polynomial. It's a different type of operation. We call that an absolute value function. This one is. Yes, it is. It has a highest degree of 8. There's a pattern here so far. Well, this is not because the x is in the exponent. That's a bad thing. And the last one is not as well because the exponent is not a whole number. Let's cross that off. Okay, so I only have to do 4 of these for the rest of them. The end behaviors. Okay, so this is a linear graph. There's a positive leading coefficient of 5. I'm going to put positive 5 here for the leading coefficient. This is a positive 5 in the leading coefficient there. And this one has a positive 4 in the leading coefficient. What you would do to determine the end behaviors is you would graph them in your graphing calculator. So if you haven't graphed them, this first one's pretty easy. It's a linear graph. It's going upwards, like that. Okay? It'd be nice what the constant terms are. I'm just going to write out the constant terms here really fast. Positive 11, positive 6, negative 4 for that one, and positive 6 for this one. Those are just the last terms. All right, those are my constant variables. Now the end behaviors, you can see this one here is going from quadrant 3 over to quadrant 1. This one is actually going from quadrant 3 to quadrant 1 as well. If you actually graphed it, you'd figure that out. This one is going from quadrant 2 to quadrant 1. That's supposed to be a 1. That looks like a 1, doesn't it? And this is the same thing. Quadrant 2 to quadrant 1. Cool. There we go. Let's go see what we have for the next questions here. Cubic. Yeah, okay. So we're going to do the same thing for these here. I want you to try these out. I'm going to give another pause. Now, try to do your best to not graph these in your calculator. See if you can actually answer some of these questions. Some of them you're going to have to because the number of x-intercepts. Everything else, except for the range of this third one at the bottom here, you can't really do. But try your best to fill out as much as you can without a graphing calculator, and then you can go to your graphing calculator, get a little sketch for it as well. Okay, pause it, try it out. All right, so hopefully you tried that out. What I can tell you about certain things about this without graphing it is I know what the maximum number of x-intercepts is going to be because it's a cubic function. The degree is 3. I'm just going to write that up here. Might as well just write that here. The degree is 3. I know the constant term is -1, which might be useful to determine the y-intercept. If I know the degree is 3, I know the max number of x-intercept is going to be 3. But I don't know if this graph actually has 3. I'm going to have to sketch it out later. I know its y-intercept is -1. And the reason I know it's -1 without graphing it is its constant term is -1. That is its y-intercept. Okay? So I can go down all of these and say, okay, this constant term is 2. So this y-intercept is 2. This constant term down here is 2. So this y-intercept is 2. Okay. The max number of y-intercepts for this one is 1. I actually know, or set x-intercepts, I know it has to have 1 because the shape of this graph, if I were to sketch this out, it looks like this. It has to cross through the x-axis once. It's not going to go back down on itself because it's a nice little linear graph. So I don't see why it would do that all of a sudden. Nice positive. I'm kind of skipping around here. I'm just doing this middle one for some reason. Has a nice positive leading coefficient. So I'm just going to write down some things about this graph before I start. So the degree is 1. The constant term is 2. The leading coefficient, I'm just going to go LC for that, is positive 3. This one, LC for this one, is negative 1. Okay. Because I know it's positive 3, it means it has to start down here and go in the positive direction up towards quadrant 3. So it starts in quadrant, sorry, 1. It starts in quadrant 3 and ends in quadrant 1. Okay. This one here is a negative coefficient. So what I know about that, if I'm not going to sketch this thing, I know it's because it's negative, it's cubic. It's going to have this shape to it, right? But it's going to be in this direction again. So it's going to go in that negative slope direction. It's cubic, so it's got to go up and down forever in both directions. So it's going to start in quadrant 2 and end in quadrant 4. Cool. Quadrant 2 and 4. Some things we just can't do right now, like what's the actual shape of this graph. What do I know about all these? These are all XER. There's no thing about these two graphs right now. Okay, the range of these two graphs are YER. The reason I know that, without looking at the graphs, is because one's a linear, one's a cubic. This one down here, that's the third one on this page here, that's a quadratic graph. That's going to have some kind of min or max point. We saw those most quadratics in Math 10 and 20. Number of turning points. Now I know the max number of turning points here is going to be 2. Max number is 2. Right? Because the graph could go up and then go from down to up and then up, down to down, but it doesn't necessarily have to do this as well. It might have a little bend, but it might just continually go down. So it might not have one at all. So it could have none or it could have 2. I don't know exactly unless I know what it is, and plus I know the degree is 3, so this is a cubic graph. This one down here, the degree is 1, so this is a linear graph. Max number of turning points. This one has no max number of turning points because it's just a straight line. The degree is 1. Again, just put in your calculator and try to graph these out and see what these look like. But what I'm going to do right now to figure out x-intercepts here. So you can see it crosses once. So I have one x-intercept. This point. This confirms my y-intercept was -1. We already knew that. And has 2 turning points. So I'm just going to go to my graph, my thing here. So number of x-intercepts, we have 1 for this one. It had a max of 3, but it only gave us 1, okay. And number of turning points, 2, okay. This one here, what do we not know about this one so far? Well, we know everything about this graph. I'm just going to show you what it looks like. 3x plus 2, so that was my graph look like there. It crosses once, has no turning points because it's a nice straight line. You can see my y-intercept was 2. So that's what that looked like. Oh, I probably should put the proper sketch here. I'll give you 2 proper sketches here. All right, so the sketch for this one. Oh no, stupid thing. X, Y, and my graph's gonna look like this. Oh, I thought I picked a different color there. Okay, this one here, if I go back to this, put this graph back in there. Let's just give that a good sketch. There you go. Cool. Okay. So this one, the next 2, I could probably try to fill as much as I can without going to the graph. So let's see. So we've got a quadratic. Okay, so what I know about this quadratic, because the leading coefficient, my LC, is -1. That's my leading coefficient. My constant term is 2. My degree is 2. So my degree is the exponent. My constant term is this last piece here. There's one down here for J. My leading coefficient is +1. If you don't see a number there, we assume it to be +1. Good assumption. Constant term is -2. This whole thing, including the negative sign, the whole thing there. And my degree is 3. Okay, so let's figure this out. So I know the max number that this quadratic could have is 2. But again, it could just touch it. It could cross twice. It could not touch at all, right? Because it's negative, my leading coefficient is negative, I know this graph is going to be opening downwards. So I know that's that shape. So for my end behaviors, I know it's going to start in quadrant 3 and end in quadrant 4. But again, you could just graph in your calculator and just do it that way. Sometimes they ask you to match certain things up. You'll see that later on. XER for my domain. My range, I'm going to have to know what this top point actually is. What I know so far is that it has to be less than or equal to some number because it's opening downwards. But we can see that from the graph later. Turning points, got to have 1. It's got to go up and then back down. All quadratics do that. And this is a quadratic, like I was saying. Cool. Okay. This is a nice cubic graph for this next one. So what I know is a positive. So it's going to go this way. I don't know if it's going to cross once or twice, but I know the max is 3. I'm going to have to figure out if it actually is 3 or not. My y-intercept here is going to be -2. This was +2 from before, okay? It starts in that quadrant down there. So that's quadrant 3. Ends in quadrant 1 up here. Domain is XER. My range is YER. You notice that it goes on down forever here, it goes up forever. These are not my sketches. I'm going to put my actual sketch here when I find the graph. The number of turning points could be 2. You know, that seems like it's always 1 less. 1 less than the actual degree. The degree is 3, the turning points is 2. Like the quadratic one here, the degree is 2, the turning points is 1. It seems like it's 1 less than that degree, but remember what I said, it doesn't necessarily have to have that. That's just the max number. This is also a cubic graph. Okay, so I'm going to pull up my graphing calculator here. What is that in my background? Oh, that's my YouTube. Okay, some science videos I was watching. So -x². Hey, look, it's opening downwards, so that's good. Plus 3x plus 2. Okay, so that's what my graph looks like there. Just going to sketch that out. So it did cross at +2, I believe. Let's look at that. Yeah, +2 as a max value. I'm going to need that max value from my range. 1.5, 4.25. That's my max point right there. Okay. It looks like it's got 2 x-intercepts as well. Let's do this cubic one down here. Ooh. Yep. Right now it doesn't have any turning points, but as soon as I add this extra piece in here, it might. Oh yeah, kind of goes up a little bit there. Just add a little extra piece in there. Oh, back to being a kind of a flattish line there. Like I was saying, it's going in that general direction here. So that because there's a positive leading coefficient. So kind of looks like that. Let's just see what we have here. Oh yeah, that's -2, like I said before. Crosses once. Okay. So let's fill out the rest of this chart. Number of x-intercepts for this quadratic, 2. My range, 4.25. So it has to be less than this value, right? Whatever value this y is, which is 4.25. And down. Okay. My cubic graph down here has 1 x-intercept and 0 turning points. It's always going upwards. It doesn't actually ever go back down, so it doesn't come back down on itself. Sometimes it does, sometimes it doesn't. The max would have been 2. In this case, there was none. Cool. Let's go down here. Now this one here is asking us to write the polynomials, right? So we're going to write the polynomials. We're going to just make one up. Doesn't really matter, just as long as it follows these general rules. And we're going to test them out at the end here. So I want to extend from 3 to 4. So my graph has got to go. It's got to go from 3. Got to have an arrow here, and then to 4. So there's got to be an arrow here. So my graph is going to look like this probably. Okay. But it's got to have a y-intercept, a positive 4. Okay, so that's going to be different. So it's got to go way up here, have a y-intercept of positive 4, which means it's going to have to cross the x-axis. So what I know about this is that, let's just call this f for now, my function. I know my leading coefficient has to be negative. It's opening down. So quadratics that have a leading coefficient that's negative would be opening downwards. That's what I mean by opening downwards, is opening upwards. So I just pick any negative number for my leading coefficient. To get this general shape, let's look at quadratics. I'm going to have an x squared there. And I want a y-intercept of 4. That would be a constant term. So I'm going to put a plus 4 here. So let's see if that actually worked. Negative x opening down. Without the plus 4, you can see that my y-intercept is 0. Cost of the origin. As soon as I put plus 4, there you go, plus 4. You can see that my y-intercept is 4. My max is actually 4 too. It has one turning point. It specifies that to you. It wants one turning point. This is the way this quadratic worked out. It always has one turning point. Okay, let's try out another one here. Extending from 3 up to 1, the y-intercept of negative 3. So it's got to cross this. It's got to go from here to here. And it's got to go, well, there you go. Why don't we just make a, doesn't say anything about turning points. Why don't we just make this a linear graph? So if I want a linear graph, it's going from 3 to 1. So this is the positive direction. So that's going to have a positive leading coefficient. So let's say 5x. And I want a y-intercept of negative 3. So I'm going to have a constant of negative 3. I could have done this as a cubed if I wanted to. I think I get the same result. We get a different shaped graph, but I get the properties it's looking for here. So let's try this out. So we got 5x or minus 3. Yeah, looks pretty good. From 3 to 1, but if I put a cube in there instead, hey, same thing. I got from 3 to 1. I got the y-intercept of 3. So either one of those works. It's pretty good. Let's see. I got a degree of 1. So it's got to be a linear graph. So we have an x, the power of 1. Okay. What else do we have in here? It's decreasing. So degree of 1 decreasing y-intercept to negative 2. So that's what decreasing is. It's going from left to right. It's going downwards. It's got to cross through at negative 2. So I know that has to be a minus 2 here. And now to get it to decrease, this is a negative slope and negative direction. So I'm going to have a negative leading coefficient. I just picked out a negative 2. It could be negative 3, negative 4, negative 5, negative pi. It could be any real number. It doesn't really matter as long as it's negative. That'll give us that shape. I'm not going to verify that one. That's too easy. I need 2 turning points and a y-intercept of 5. 2 turning points. So I need to have a turning point going to go like this and like this. So maybe something like that. That looks cubic to me, so I'm going to say this is cubic. The way I drew this is positive. I don't think it necessarily has to be positive because it doesn't say which quadrants it's going from. So I just drew it positive. So let's just say that's x. Let's put a 2 there. I have to have a y-intercept of 5. Now let's graph this. The reason I put a big space in there is because if I graph this, I can just get rid of this piece here. Okay, I graph this. I don't think I'm going to get my 2 turning points. Plus 5. Yeah, so that graph there doesn't have 2 turning points. It only has, it has actually no turning points. I need 2 turning points. So I need to just jam something else in here. That seemed like it worked. Yeah, that works. So I'll put like a negative 5x in there. Would it work if I put a positive 5x in there? No, seems like it would have been negative. So this is just more guess check to find out if you try to get those two. I'm just going to throw in something in there, see if it works. If it does, then if it doesn't, then pick something else to put in there. Maybe I could put a square in there. I don't know if that would work for us. Oh yeah, 5x squared would work as well. Yeah. But that would give us the 2 turning points we need. There you go. Looking pretty good. Cool. Okay, so there's a few more questions here. These are kind of test questions, and then the next video we'll talk about word problems and the domain and range of these kind of questions in the next video. But let's look at these questions here really quickly. This is just a matching one. So I got 4 quadratics here. I got 4 quadratics up here. I want to match them up. Now, the best way to match these up is just to graph them in a calculator. Yeah, anyway, so let's just worry about this. Now, these two here, these guys are in standard form. Everything we've been doing so far is in standard form. So I'm just going to look at these two right now. I can just, by process elimination, maybe figure out which of these two graphs are which. Nope, maybe I can't. Not very nice. Okay, this one at the bottom is in factored form. The reason I can't just figure out which is 1 and 2, or I and I, is because everything here, all these graphs have a y-intercept of positive 4. And because the constant values here are 4, these have y-intercepts of 4, but apparently everything just has a y-intercept of positive 4. This last one here is in factored form. Factored form is really useful because if I make the y is equal to 0, like we did in previous classes, I can figure out what would make this equal to 0. Remember, if I want to find my y is equal to 0, so if I make y is equal to 0, I'm finding my x-intercepts. If I make this y is equal to 0 and it's in factored form, -1 would make this 0 and -2 would make this 0. So those are my 2 x-intercepts. So I'm just going to go down here and just look at these graphs. I want to know which one of these has -2, -1. Graph number 3. So graph number 3 is graph 4. Okay, so I can get rid of that graph right now. Good. I don't know if you guys remember vertex form from previous classes. Vertex forms helps us find out where the vertex of a quadratic is. These two numbers here, the -1 and the 7, -1 and the 7, that is your vertex. That's what this standard form is. You can't really see it there. It'd be backwards, but it's right there. This is backwards, but that's vertex form. It's been seen in my classroom for a while. Okay. Cool. So that's where the vertex, -1, 7. So I can look at some of these. Oh, sorry, not -1 and 7. +1 and 7. The negative should be this. It's +1 and 7. Oh, that's this graph here. Let's see if right up here. This is +1, 7. So this is graph 2. Okay. Now the other one's graph 1 and 2. I could just look at these and say, okay, the leading coefficient number 1 is positive, so this has to be opening upwards. The last graph opening upwards. This one. So my process elimination, let's just double check. Leading coefficient is -1, so it's opening downwards. Oh, it's freaking out. So that's graph 2. There you go. There we go. Okay, so we have 8 graphs here. I want to know which of these graphs match up with what we have down here. Now, so figure out what graphs match up with these. I'm just going to try my best to keep this where it is. Graph 3, I lose my top 2 graphs. So that's okay. I can probably zoom out. There we go. Okay, so for graph number 1, the first one here. This is a linear graph. You can see that my exponent, the degree is 1, so it's got to be 5, 6, 7, or 8. One of those graphs there. Its a and b values are greater than 0. So my leading coefficient is greater than 0. I'm going to sneeze. Excuse me. Okay, so if my leading coefficient is greater than 0, that means I'm going to have this kind of slope. That's my positive slope. So it's got to be 5 or 6. And my b value, which is my constant term here, that's my b value there, is greater than 0. So that means my y-intercept is also greater than 0, which is a positive number. So this is graph 5, right? Positive number, positive leading coefficient. So everything there is positive. Okay, let's check this next one here. So they're saying they're both negative. A and B are both negative, so that means they're going downward. So this is the slope of negative. This is the slope of negative, okay? And this b value is less than 0 here, so that's negative. This one here is positive. Actually, I'm just going to list them all out like that, I guess. Makes me make it a little bit faster later on. Okay, so they both have to be negative here. So a comma b is less than 0. So all that means everything's negative, so that's graph 7. Okay. The next two are quadratics. A and C are both positive. So that means since A is positive, that means the graph is opening upwards. So this is positive, positive, negative, negative. Okay. And C is positive, so that means my y-intercept is also positive. Because in this case, C is my constant term, not B. B is that weird middle thing. That does describe parts of the shape, but we're not too concerned about that for this course. They're both positive, so both positive would be graph 3. In this case, A and C are negative. It's a different way of writing it. A is negative, C is negative, so they're both negative. That would be graph 2. There you go. The next one should be pretty easy then, because I've already listed off positive and negatives here. So a linear graph that has a negative A, but a positive B. So that's graph 8. Positive A, negative B. So that's graph 6. Okay. Kind of process elimination there anyway. Positive A, so no, negative A, so opening down. So one of the first two graphs, and positive C. So that's graph 1. And this one's opening upwards because it's positive A, but as a negative constant value. Oh, so this one here, I don't know why I wrote negative. There you go, that should be there. So graph 4. There we go. Okay, so the next video we'll talk about word problems. I'll see you then.